Ardila, again on massive galaxies, early types, and mass profiles.
Hello, everyone. Can you hear me? Yeah. Okay. Yes, hello. My name is Felipe Ardila. I am a graduate student here at UC Santa Cruz, and I will be telling you about some of the work I've been doing studying the stellar profiles of massive galaxies, comparing hypersubprime-cam observations with data from the hydrodynamic simulations, and in particular for this talk, I will focus on Illustris and Illustris TNG. And this is work that I've been doing with Alexei Liotho and Song Huang, and also in collaboration with all of the people listed here, some of whom are here this week. So we heard from Song yesterday about his work studying the stellar profiles of massive galaxies in HSC. So I won't go into a lot of the details about the technique there, but the important point to make here is that we're using the same methodology to analyze both our HSC observations and our simulation galaxies. And so this allows for a consistent comparison between the two. And just to remind everybody about our mass definitions, I'm going to borrow some images from Song's talk. Essentially we draw isophotes, elliptical isophotes, so with fixed ellipticity around each of our galaxies, and we measure the amounts of mass contained at a given radius along each isophote. And this allows us to build projected stellar mass profiles for each galaxy. And so in order to measure the mass within a given radius, we simply integrate the profile out to that radius. So we're able to obtain the mass within 100 kpc or within 10 kpc or any radius really that we want. And another advantage of using HSC data is that we're able to use weak lensing to measure the masses of the dark matter halos that these central galaxies live in. And oftentimes these halos extend far beyond the stellar halos of the galaxies. So this is very useful. So in this way, we're able to plot this stellar to halo mass relation for our HSC sample. And so, like I said, we use weak lensing to get the mass of the halo. We integrate the stellar mass profile to get the stellar mass within 100 kpc. And this is where our HSC sample, it's complete to this area. And this is where they live. So we can start comparing to our simulations. So we look at our Illustris sample. We see that there's quite a bit of offset from the HSC galaxies. And if instead we look at TNG, the picture's a little bit different. So in this lower mass bin between 10 to the 13 and 10 to the 13.4 solar masses, there seems to be a lot of consistency between TNG and HSC. But as you go to higher and higher halo mass, the difference between the two increases. So we'd like to try to understand what is the reason for this difference, what is causing this offset in mass. And so the first thing we can do is look at the stellar profiles directly. And we can look at the stellar profiles for each halo mass bin. So here, for instance, we're looking at the stellar profiles for this first halo mass bin. So this is between 13 and 13.4. So 10 to the 13, 10 to the 13.4 solar masses. And we're plotting projected stellar mass surface density versus radius to the 1/4, or radius in kiloparsecs up top. And we see that the profiles are very consistent between the two. So TNG is in blue, HSC is in black, and there's a lot of agreement, and so much that the stellar mass within 100 kpc agree very well with each other. And we see that in this plot here. They're almost identical. But if we instead look at the profiles at the higher halo mass bins, so for instance, this middle plot is looking at the halo masses between 13.4 and 13.8. And we see that there seems to be agreement in the inner parts of the galaxy. So this inner part seems to be very similar between HSC and TNG. But after around 30 kpc, the HSC profile falls off much more quickly than the TNG profile. So that's telling us that there is more mass in the outer regions of the TNG galaxies than we observe in HSC. And the difference is even more striking in this higher halo mass bin. So again, we see that there's this large offset in the outer regions, but there's also systematic offset in the profile toward higher masses for the TNG profile compared to our HSC profile. And another way to kind of look at the same picture here, the same idea, is to study the stellar mass functions. So here we're plotting masses within 10 kpc, within 30 kpc, and within 100 kpc. HSC is in black, Illustrious is in red, TNG is in blue, and the rest are some of the other hydrodynamic simulations that we've begun to look at. And I think what this is telling us is a consistent picture as before. The simulations seem to agree well with our HSC observations. For the inner regions of galaxies, the masses agree well in the inner regions. But as you go to higher and higher radii, they start to diverge, and there we see more of a difference between simulations and our HSC observations. So what is the reason for this difference? Is it overmerging? Is there something in the AGN feedback recipe? Something else that we don't know? Well, one of the things we'd like to do to try to understand this better is to get X-ray data for our HSC observations. And this X-ray data will help us to understand some of the baryonic effects that may be affecting the growth of these galaxies, the distribution of stellar mass, and maybe better understand the AGN feedback as well. And then we could go back and better calibrate our simulations to these observations and try to match the profiles even better. And I think I've gone a little fast, but if I can leave you with one takeaway from my talk, it would be this, that the stellar profiles of massive galaxies in hydro simulations, they agree well with our observations in the inner regions of galaxies, but as you go out to the outer regions, these simulations seem to have too much mass in their extended stellar envelope, so the agreement is not so well in the outer regions. Thank you.
Thank you. Questions? Yep.
So I think the apples to apples comparison is great. I was wondering about two things maybe. The first is mass versus light. So you mentioned, I think you're using just mass from the simulations, but
Yes.
of course we can give you directly light in the observed bands, including attenuation effects, so maybe that could be important. The other thing is about the satellites, the masking. So as I remember in HSC, you have this fairly complex procedure to take out projected satellites and stuff. So is that also done in the same way with the simulations?
No, so like you said, in HSC, it's a pretty complex procedure to mask out all the satellites. In the simulations, we do it a little bit differently. We kind of just exclude satellites from the beginning and only focus on the central galaxy, and that's really all we're measuring. So it is a little bit different.
Do you have a guess how that would move?
We actually have done tests to check how much it changes, and the difference is very little, and it's really more in the outer regions of the galaxy. So it's very small, actually.
So if you think that comparison is really robust, what changes to the feedback do you think could result in this difference?
Honestly, that's something I'm not an expert in at all, so I wouldn't be able to tell you, but maybe somebody else in this room has some ideas. I don't know.
James.
I have a conjecture based on very little, but what do you think about this? Things work pretty well at Z of 0 at these lower masses. So you might wonder, well, how is it possibly not working at the higher masses since it's just a hierarchical thing and you're just shredding galaxies? But maybe it's pointing to the fact that maybe something's wrong at higher redshift because the things that are building this intracluster light are things that were created earlier, and so maybe in the simulations they just have a little bit too much mass at early times, so they fall in and they shred out, and so it might be an evolutionary thing that you're picking up at high redshift because you're probing sort of a higher redshift population.
Yeah, it's interesting. Thank
Okay, one last question, comment.
Can you comment on the ellipticity and perhaps the changes in the position angle of the major axis for these systems? Because that will affect your profiles, and so there's a difference in, let's say, the shapes. I can imagine affecting things. But I don't hear much about the ellipticity distribution consistency nor the PA changes.
Yeah. So the ellipticity does change depending on the mass of these objects. And in some of our other plots, we make these profiles and plot them side by side with the ellipticity. That's something I haven't done here, but essentially it is something that we take into account. But for our isophotes, the ellipticity is fixed to prevent twisting. Yeah.
Okay, one last question while we set up the next speaker. No? Okay, yeah.
Follow-up, yeah, so are the shapes of the observed and simulated galaxies the same? And if you do spherical profiles, do they agree better or worse?
I'm not actually sure how to answer that. I'll get back to you.